Right now, astronomers can measure stars so enormous that their surfaces would extend beyond the orbit of Jupiter, and the largest one ever confirmed, Stephenson 2-18, forces us to reconsider what the word possible means in stellar physics. By the end of this video, you'll understand why finding the upper limit of star size is one of the most precise tests we have of how fusion, gravity, and radiation interact under extreme conditions. If this is the kind of science you like, subscribe for more breakdowns like this. Let's break it down, step by step. Stephenson 2-18 sits roughly 19,000 light-years away in the constellation Scutum. When astronomers measured its radius using infrared interferometry and spectroscopic analysis, they arrived at a value between 2,000 and 2,600 times the radius of our Sun. To clarify what that means in everyday terms, if you place Stephenson 2-18 where the Sun is, its outer layers would reach somewhere between the orbit of Saturn and beyond. The measurement comes from combining angular diameter data with distance estimates derived from its association with the Stephenson 2-star cluster and its radial velocity. The uncertainty range is large because measuring the size of a red supergiant is not straightforward. These stars have diffuse, unstable atmospheres that blur the boundary between surface and space. What we're actually measuring is the photosphere, the layer where the star becomes opaque to light, and that layer shifts depending on wavelength and time. So when we say Stephenson 2-18 is the biggest star, we mean it has the largest, reliably estimated photospheric radius among confirmed stars, with the caveat that the exact number depends on the measurement technique. Notice what that uncertainty tells us about the problem. The question is not just how big a star can get, it's why stars have an upper size limit at all. Stars form when clouds of hydrogen collapse under gravity, and fusion begins in the core. As mass increases, core temperature rises, fusion accelerates, and the star produces more energy. For most stars, hydrostatic equilibrium keeps them stable. Gravity pulls inward. Radiation pressure from fusion pushes outward. But above a certain mass, radiation pressure becomes so intense that it starts to tear the outer layers apart. This is called the Eddington limit, and it constrains how luminous a star can be for a given mass. Red supergiants like Stephenson 2-18 are not the most massive stars. They are evolved stars that began with perhaps 16 to 25 solar masses and have exhausted the hydrogen in their cores. After core hydrogen runs out, the core contracts and heats up, igniting helium fusion. Meanwhile, the outer envelope expands enormously and cools, turning the star red. The radius expands because the energy from shell burning pushes the envelope outward, faster than gravity can pull it back. The result is a star with a relatively modest core mass, but a bloated atmosphere extending billions of kilometers. Here's what that process reveals about stellar structure. Red supergiants are unstable by design. Their outer layers are so loosely bound that slight changes in luminosity or temperature can trigger enormous pulsations, mass loss, or even partial ejection of the envelope. Observations of Stephenson 2-18 show variability in brightness, consistent with pulsations driven by opacity, changes in the outer layers. As the photosphere expands and cools, it becomes more opaque to certain wavelengths, trapping energy and causing the layer to heat and re-expand. This feedback loop is what allows red supergiants to reach such extreme sizes, but it also makes them short-lived in this phase. Stellar evolution models suggest that a star spends only a few 100,000 years as a red supergiant, a blink compared to the billions of years it spent on the main sequence. Stephenson 2-18 is likely near the end of this phase, possibly within a few thousand years of core collapse. The next step in its evolution is either a supernova, if the core mass exceeds the threshold for iron photodissociation, or direct collapse into a black hole if mass loss has been insufficient. What evidence would tell us which path it will take? Core mass is the key variable. If the helium core retains more than roughly 10 to 15 solar masses by the time silicon burning ends, the core will exceed the electron degeneracy pressure limit and collapse directly. If mass loss has reduced the core below that threshold, the supernova mechanism can proceed, ejecting the envelope and leaving behind a neutron star. Estimating the current core mass of Stephenson 2-18 requires modeling its entire evolutionary history: initial mass, rotation, metallicity, mass loss rate, and the timing of each burning stage. Spectroscopic measurements give us surface composition, which tells us what elements have been dredged up from the core during convective mixing. The presence of nitrogen and carbon enhancement suggests CNO cycle processing, and possibly some helium-burning products. But translating surface abundances into a core mass estimate involves assumptions about mixing efficiency and mass loss history, both of which are uncertain. What we can say with confidence is that Stephenson 2-18 has already lost a significant fraction of its initial mass through stellar winds, driven by radiation pressure on dust grains in its cool outer atmosphere. Infrared observations reveal a circumstellar shell of ejected material, consistent with mass loss rates on the order of 1/10,000th of a solar mass per year. Keep that number in mind. Mass loss sets the effective upper limit on red supergiant size. As the radius increases, the gravitational binding energy of the outer layers decreases. At some point, radiation pressure and pulsation-driven shocks can levitate material away from the star faster than the star can replace it through envelope expansion. This is why we don't see red supergiants with radii of 5,000 or 10,000 solar radii. They would simply blow themselves apart. The largest red supergiants cluster around 2,000 to 2,600 solar radii, because that's where the balance between expansion and mass loss stabilizes. Stars that try to grow larger lose mass so rapidly that they shrink back down or transition to a different evolutionary phase. Observations of other extreme red supergiants like UY Scuti and VY Canis Majoris show similar size ranges and similar evidence of extensive mass loss in circumstellar shells. The consistency across multiple objects suggests we are seeing a real physical boundary, not a measurement artifact. So what determines where exactly that boundary lies? Metallicity is one factor. Stars with higher metallicity have more dust-forming elements like carbon, oxygen, and silicon in their atmospheres. Dust grains are efficient at absorbing ultraviolet and optical photons and re-radiating them in the infrared, which increases the coupling between radiation and matter. This makes radiation-driven winds more effective, increasing mass loss rates and potentially limiting how large the envelope can grow. Stephenson 2-18 formed in a region of the galaxy with near-solar metallicity, which means it has access to efficient dust-driven winds. Lower metallicity stars, like those in the early universe or in metal-poor dwarf galaxies, might evolve differently. With weaker winds, they could retain more mass and potentially reach different maximum sizes, though they would also face different core-burning timescales and mixing efficiencies. Population 3 stars, the first generation with zero metals, are thought to have been extremely massive, but likely did not become red supergiants. Instead, they probably evolved as blue supergiants or Wolf-Rayet stars, and ended as pair instability, supernovae. The dependence on metallicity illustrates how stellar evolution is not universal, but context-dependent. Here's why that matters for interpreting what we see today. When we observe a red supergiant like Stephenson 2-18, we are seeing a snapshot of a process that unfolds over thousands of years, embedded in an environment that shaped its formation billions of years ago. The star's current radius is the result of its initial mass, the composition of the gas cloud it formed from, its rotation rate, whether it had a binary companion that stripped mass or added angular momentum, and the history of mass loss throughout its main sequence and post-main sequence evolution. Each of those factors is constrained, but not perfectly known. Initial mass is estimated from evolutionary tracks that fit the current luminosity and temperature. Distance is estimated from cluster membership and spectroscopic parallax. Radius is inferred from angular diameter measurements that assume a spherical, limb-darkened photosphere. Every step introduces uncertainty. The range of 2,000 to 2,600 solar radii reflects the compounding of those uncertainties. Alternative models that assume different mixing lengths or mass loss prescriptions can shift the radius estimate by 10 to 20%. What measurement would reduce that uncertainty? Direct imaging with interferometry at multiple wavelengths would help. Infrared interferometry resolves the angular size of the photosphere, but the photosphere's apparent size changes with wavelength because different layers become opaque at different temperatures. Observing Stephenson 2-18 in the near-infrared, mid-infrared, and submillimeter would map the temperature structure of the outer envelope and constrain the density profile. Combining that with time-series photometry and spectroscopy to track pulsations would reveal the dynamical state of the star, whether it is in a quasi-steady expansion or undergoing episodic mass ejections. High-resolution spectroscopy could measure the velocity of the outflowing wind directly via Doppler shifts in molecular absorption lines, which would constrain the mass loss rate independently of dust models. And if we could measure the distance to the Stephenson 2 cluster more precisely using Gaia parallax data for cluster members, or geometric distances from masers in associated star-forming regions, the radius uncertainty would shrink proportionally. Look at what that reveals about the method. The challenge is that Stephenson 2-18 is deeply embedded in the galactic plane, surrounded by dust and crowded star fields that complicate both photometry and astrometry. Gaia's parallax measurements are less reliable for faint, reddened stars in crowded regions, so the distance estimate relies partly on kinematic models and partly on the assumption that the star is physically associated with the Stephenson 2 cluster. If the star is actually in the foreground or background of the cluster, the radius estimate would need to be rescaled. Spectroscopic studies have confirmed that Stephenson 2-18 shares the cluster's radial velocity, which supports cluster membership, but radial velocity alone cannot rule out line-of-sight coincidences. The best confirmation would come from measuring proper motion or trigonometric parallax directly, but the star's faintness and heavy extinction make this difficult even for Gaia. So we proceed with the best available data and acknowledge the limits. Now zoom out to the broader question. Why does finding the largest star matter beyond the object itself? Because the maximum size of a red supergiant is a testable prediction of stellar evolution theory. Models of post-main sequence evolution must account for convection, mass loss, rotation, and nuclear burning in shells around an inert core. Each of these processes depends on microphysics, opacity tables that describe how radiation interacts with matter, nuclear reaction rates measured in labs, equations of state for partially ionized plasmas, and prescriptions for turbulent convection that cannot be resolved directly. When we observe a star at the edge of the allowed parameter space, we are testing whether all those inputs are correct. If red supergiants were routinely found with radii of 5,000 solar radii or 10 solar radii, it would indicate that something in the models is wrong. Either the mass loss rates are underestimated, or the mixing efficiency is different, or that the opacity calculations are off. The fact that the largest red supergiants cluster tightly around 2,000 solar radii, and that models predict roughly that same limit, is a successful prediction. But successful predictions are only as good as the data that confirm them. What does the clustering itself tell us? It suggests that red supergiant evolution converges toward a common endpoint regardless of the initial conditions, as long as the metallicity is similar. Stars with initial masses from 15 to 25 solar masses all seem to pass through a red supergiant phase and reach similar maximum radii, even though their core structures and lifetimes differ. This convergence happens because the mechanisms controlling size, radiation-driven mass loss and pulsational instability, depend primarily on the surface conditions, not the core. A star with a 15 solar mass helium core and a star with a 20 solar mass helium core can both develop cool, extended envelopes that reach the mass loss threshold at roughly the same radius. The difference lies in how long they stay in that phase and what they leave behind after core collapse. Stars on the lower end of the mass range may produce neutron stars and type 2p supernovae with long plateau phases. Stars on the higher end may collapse directly or produce type 2L or 2b supernovae with faster light curve declines. Stephenson 2-18's final fate depends on details we cannot yet measure from the outside. Here's what would settle it. If we could observe the neutrino flux from the core in real time, we could infer the core temperature and burning stage. Neutrinos escape the core directly without interacting, carrying information about the nuclear reactions happening deep inside. For a star in late helium or carbon burning, the neutrino luminosity would be comparable to the photon luminosity. For a star in neon or oxygen burning, neutrinos would dominate. Current neutrino detectors are not sensitive enough to detect neutrinos from individual stars at kiloparsec distances, except during the brief seconds of core collapse when the neutrino flux spikes by orders of magnitude. Supernova neutrinos have been detected exactly once, from SN 19827A, and even that required a star in the nearby Large Magellanic Cloud. Stephenson 2-18 is too far and too dim in neutrinos to be monitored continuously, so we rely on indirect tracers. Variability in the optical and infrared light curve can indicate pulsation modes that correlate with core burning stages. Spectroscopic changes in surface composition can signal recent dredge-up events, and the morphology of the circumstellar shell can reveal the history of mass ejections. Each piece of evidence constrains the possible evolutionary tracks. Notice how this connects back to size. The radius of a red supergiant is not a static number. It changes over the course of the red supergiant phase as the star cycles through different shell-burning episodes. After core helium exhaustion, the core contracts until carbon ignites. This releases energy, temporarily halting the contraction and possibly causing the envelope to re-expand. After carbon burns out, the core contracts again and neon burning begins. Each ignition phase can trigger a new pulse of expansion or mass loss. Some models predict that red supergiants undergo episodic dimming events, where dust formation in the extended atmosphere temporarily obscures the photosphere, causing the apparent radius and luminosity to drop. VY Canis, Majoris, and Betelgeuse have both shown such dimming events in recent years, interpreted as transient dust clouds passing through our line of sight. If Stephenson 2-18 undergoes similar events, the measured radius at any given time might not represent the long-term average, but rather a snapshot of a pulsation cycle. Time domain astronomy is essential for understanding these objects. What does that mean for our measurement of the biggest star? It means the title is provisional. Stephenson 2-18 holds the record based on current data, but the measurement uncertainty overlaps with several other candidates, Uwasi Scuti WOHG 64 and Westerlund 1W26. All of these stars have estimated radii in the range of 1,800 to 2,600 solar radii, and the error bars are large enough that any one of them could be the largest, depending on which measurement technique and model assumptions you use. The choice of biggest is somewhat arbitrary. What matters scientifically is that these stars all occupy the same region of parameter space, which tells us something consistent about the physics. Rather than competing for a title, they collectively define the boundary. If future measurements revise the radius of Stephenson 2-18 downward and move another star to the top of the list, the underlying conclusion remains. Red supergiants max out at around 2,000 to 2,600 solar radii under current galactic conditions. So what would it take to find a genuinely larger star? You would need either a lower metallicity environment where weaker winds allow the envelope to grow larger, or a star with an unusually high rotation rate, which could alter the effective gravity and allow more expansion, or a binary interaction that stripped the envelope and then reaccreted mass in an unusual configuration. Each of these scenarios is rare but possible. The early universe, before the first generations of stars had synthesized and distributed metals, might have produced red supergiants with different maximum sizes, though as mentioned earlier, the most massive population 3 stars likely evolved differently and avoided the red supergiant phase entirely. In the present-day universe, the best places to look for extreme red supergiants are in star-forming regions, with active massive star production and in environments with varied metallicity. The Large Magellanic Cloud has been surveyed extensively and hosts several extreme red supergiants, though none currently exceed Stephenson 2-18 in estimated radius. Future infrared surveys with JWST and ground-based interferometers will continue to refine the census. Here's why that census matters beyond record-keeping. Red supergiants are the primary factories of heavy elements in the universe. During their main sequence lifetimes, massive stars produce carbon, nitrogen, and oxygen through CNO cycling and helium burning. During the red supergiant phase, convective dredge-up brings those processed elements to the surface, and mass loss disperses them into the surrounding interstellar medium. When the star finally explodes as a supernova, The core collapse mechanism synthesizes even heavier elements through rapid neutron capture and explosive nucleosynthesis, and the explosion ejects those elements at high velocity, enriching the next generation of star-forming clouds. Stephenson 2-18 has already contributed to this cycle through its wind-driven mass loss. The circumstellar shell contains carbon-rich dust and molecules like carbon monoxide, water vapor, and silicon monoxide, all of which formed in the waste cooling outflow. If the star goes supernova in the near future, it will add iron peak elements and possibly R process elements to the galactic inventory. The rate at which this happens depends on how many red supergiants exist at any given time and how long they spend in the mass-losing phase. What does the observed population tell us? There are only a few dozen confirmed red supergiants with radii exceeding 1,500 solar radii in the entire Milky Way and nearby galaxies. This scarcity reflects two things. First, the red supergiant phase is brief, so the number of stars in that phase at any moment is small. And second, the progenitor stars are massive and rare to begin with. Stars massive enough to become red supergiants represent less than 1% of all stars formed, and the most extreme red supergiants come from the upper end of that mass range, making them even rarer. Additionally, red supergiants are heavily obscured by dust and are most easily detected in the infrared, so detection biases may be hiding some of them. Infrared surveys like 2MASS and WISE have identified many previously unknown red supergiants, and JWST sensitivity in the mid-infrared is expected to reveal more. The current sample is likely incomplete, especially in the most distant and dust-obscured regions of the galaxy. As the sample improves, we will get a better handle on the initial mass function at the high end, and on the dependence of red supergiant properties on environment. Keep that in mind as we consider the next question. How does the existence of stars this large affect the structure and evolution of star clusters? The Stephenson 2 cluster, where Stephenson 2-18 resides, is an open cluster containing more than 20 red supergiants along with other massive stars in various evolutionary stages. The concentration of red supergiants suggests the cluster underwent a burst of star formation roughly 10 to 20 million years ago, and the most massive stars are now in their post-main sequence phases. The combined mass loss from all these red supergiants injects energy and momentum into the cluster environment, potentially driving turbulence and shaping the residual gas distribution. If multiple stars in the cluster explode as supernovae within a short time span, the cumulative energy input could unbind the cluster entirely, dispersing the remaining stars into the galactic field. Observations of the cluster's velocity dispersion and spatial distribution can test whether this process is already underway. The presence of a circumstellar shell around Stephenson 2-18 indicates localized mass loss, but the cluster-wide effects depend on the total mass loss budget of all the red supergiants combined. What measurement would clarify this? Mapping the spatial distribution and kinematics of gas and dust in the cluster using submillimeter and radio observations would reveal whether there is a cluster-scale outflow or shocked shell driven by stellar winds and past supernovae. CO and HI, line emission would trace the cold gas. Dust continuum emission in the far infrared would trace the warm dust. And X-ray observations might detect hot shocked gas from wind collisions. If the cluster is gravitationally bound despite the ongoing mass loss, it suggests that the initial cluster mass was high enough to retain the stars, even as the gas is expelled. If the cluster is expanding, it suggests that the gas expulsion has reduced the gravitational potential below the binding threshold. Either way, Stephenson 2 represents a laboratory for studying how massive stars feed back into their birth environments. Now let's return to the star itself. One unresolved question is whether Stephenson 2-18 has a companion. Binary interactions can dramatically alter the evolution of massive stars by transferring mass from one star to the other, or by tidally spinning up the rotation rate. If Stephenson 2-18 is part of a binary system, the companion could have stripped some of the envelope during an earlier phase of mass transfer, reducing the total mass and changing the core structure. Alternatively, if the companion is a lower mass star, it might simply be orbiting in the extended envelope, accreting material from the red supergiant's wind and possibly forming an accretion disk. Such systems are rare but known, They often produce complex circumstellar structures and variable emission as the companion perturbs the wind. Spectroscopic monitoring for radial velocity variations could detect a companion if the orbital period is short enough, but long-period binaries with separations of hundreds of astronomical units would require decades of observation to confirm. Imaging at high resolution with adaptive optics or interferometry might resolve a companion directly if it is bright enough and separated by at least a few tens of milliarcoseconds. Current data do not show clear evidence of a companion, but the observations are not deep or long baseline enough to rule one out. So what does that uncertainty imply? It means we cannot fully reconstruct Stephenson 2-18's evolutionary history without additional constraints. Single-star models provide a baseline, but binary evolution introduces additional free parameters that can shift the predicted radius and luminosity. If the star did experience binary interaction, the current radius might be either larger or smaller than the single-star prediction, depending on the timing and efficiency of mass transfer. The presence of a circumstellar shell without obvious asymmetries suggests that recent mass loss has been relatively spherical, which is more consistent with a single star or a wide binary than with an active mass transfer system. But past interactions could still have left a signature in the core structure or surface composition. Detailed abundance measurements of heavy elements and isotope ratios could discriminate between single star and binary-influenced evolution, since binary mass transfer can alter the surface abundances in ways that differ from standard dredge-up. Here's what to watch for in future observations. If follow-up spectroscopy detects anomalous abundances, such as enhanced helium or nitrogen without corresponding carbon enhancement, or unexpected isotope ratios of carbon or oxygen, that would suggest a non-standard mixing history, possibly driven by rotation or binary interaction. If long-term photometric monitoring reveals eclipses or periodic modulation of the light curve, that would confirm a companion. And if JWST imaging in the mid-infrared resolve structure in the circumstellar shell that suggests asymmetry or spiral patterns, that could indicate a binary wind collision zone. Each of these tests is feasible with current or near-future facilities. The key is to obtain high signal-to-noise data over multiple epochs to separate intrinsic stellar variability from binary effects. Notice how each piece of evidence narrows the possibilities. This step-by-step refinement is how astrophysics works. We start with a basic observation, a very large, very luminous star. We estimate its distance, measure its angular size, calculate its radius, and place it in the context of stellar evolution theory. The initial measurement has large uncertainties, so we design follow-up observations to reduce those uncertainties and test alternative explanations. We compare the object to similar objects to see if it is unique or representative of a population. We build models to predict what we should see if our theoretical understanding is correct, and we look for discrepancies that might indicate new physics or missing processes. When discrepancies appear, we refine the models or revise the observations. The process is iterative and self-correcting. Stephenson 2-18 fits comfortably within this process. It is an extreme object, but it is not inexplicable. What it reveals about stellar physics is both confirmatory and generative. Confirmatory in the sense that it matches the predictions of red supergiant evolution, a post-main sequence star with a bloated envelope, strong mass loss, and a size consistent with the radiation-driven wind limit. Generative in the sense that it raises new questions about the details. Exactly how does convection work in such an extended envelope? How do pulsations couple to mass loss? What is the role of magnetic fields? How does rotation affect the structure? And what determines the precise timing of core collapse? Each of these questions is an active area of research, and objects like Stephenson 2-18 provide the observational anchor points. Without extreme cases, we would not know where the boundaries lie. With them, we can map the allowed parameter space and probe the physics at the edges. Here's how that connects to the larger picture. The study of stellar extremes is part of a broader effort to understand the diversity of cosmic phenomena. Stars range from red dwarfs with 1/10 the mass of the Sun, which burn hydrogen for trillions of years, to hypergiants with hundreds of solar masses, which live for only a few million years and end in pair instability explosions. The universe produces both, and everything in between, because the laws of physics permit it. The initial mass function, the distribution of stellar masses at formation, is weighted toward low-mass stars, but high-mass stars dominate the energy budget and chemical evolution of galaxies, despite their rarity. Understanding the full range is essential for modeling galaxy evolution, the cosmic star formation history, and the origin of the elements. Stephenson, 2-18 is one data point in that larger story. Its size tells us about the physics of envelope expansion and mass loss. Its luminosity tells us about the efficiency of nuclear burning in high-mass stars. Its spectrum tells us about nucleosynthesis and mixing. And its eventual supernova will tell us about the mechanism of core collapse and the production of heavy elements. Each aspect contributes to our understanding of how stars work. What comes next in the research? The next generation of instruments will allow more precise measurements of red supergiant properties. JWST's mid-infrared capabilities will map the temperature and composition of circumstellar shells in unprecedented detail, revealing the geometry of mass loss and the formation sites of dust. Extremely large telescopes like the Extremely Large Telescope and the 30-meter telescope will provide high-resolution spectroscopy to measure wind velocities and surface abundances with greater accuracy. Interferometric arrays will improve angular resolution, reducing the uncertainty in radius measurements. And time domain surveys will track the variability of red supergiants over years to decades, capturing pulsation cycles and potential pre-supernova outbursts. When Stephenson 2-18 does go supernova, if humanity is still watching, the data will be invaluable. The light curve, spectrum, and neutrino signal will constrain the progenitor mass, the explosion energy, the nickel mass produced, and the structure of the circumstellar medium. Comparing that data to the pre-supernova observations will test whether our models correctly predicted the star's internal state. Look at what that tells us about the scientific process. Astronomy is fundamentally a waiting game. We cannot control the stars. We can only observe them and wait for them to change. Red supergiants are among the few objects where the timescale of change is short enough that we might see it within a human lifetime. Betelgeuse, the nearest red supergiant to Earth at about 500 light-years, has already shown signs of instability, including the dramatic dimming event in late 2019 to early 2020. That event prompted speculation that Betelgeuse was about to explode, though follow-up observations showed the dimming was most likely caused by a transient dust cloud rather than an imminent core collapse. Betelgeuse will go supernova eventually, but the uncertainty in the timing is still thousands of years. Stephenson 2-18 is farther away and less well studied, so the timing uncertainty is even larger. What we can say is that it is in the final stages of its life, and it could explode at any time on astronomical timescales. Whether that happens tomorrow or 10,000 years from now, the star is already providing valuable data simply by existing. Here's why that data matters. Every red supergiant we observe adds to the statistical sample that constrains stellar evolution theory. Individual objects have large uncertainties, but the ensemble properties, such as the distribution of radii, the correlation between radius and luminosity, the frequency of pulsations, the mass loss rates, and the surface compositions, are more robust. By comparing the observed distributions to the predictions of population synthesis models, we can test whether the input physics is correct. If the models predict too many large red supergiants or too few, it indicates a problem with the mass loss prescription or the initial mass function. If the predicted distribution of surface abundances does not match observations, it suggests that the mixing models need adjustment. Stephenson 2-18 is part of that ensemble. Its extreme size makes it particularly valuable because it tests the upper boundary of the distribution. If the boundary were different from what we observe, it would force a revision of the theory. The fact that the boundary aligns with theoretical predictions is reassuring, but it is not the end of the story. What questions remain open? One major uncertainty is the role of rotation. Massive stars often rotate rapidly, and rotation affects both the structure of the star and the efficiency of mixing. Rotationally induced mixing can bring fresh hydrogen from the envelope into the core, extending the main sequence lifetime and altering the surface abundances. During the post-main sequence phase, rotation can also affect the envelope expansion, by changing the effective gravity at the stellar equator. A rapidly rotating red supergiant might be oblate, with a larger radius at the equator than at the poles, and might shed mass preferentially from the equator, creating an asymmetric circumstellar shell. Observations of rotating red supergiants are challenging because the rotation velocities are typically low in absolute terms due to the large radius. Even if the angular momentum is high, the surface velocity is diluted by the enormous moment of inertia. Measuring rotation requires high-resolution spectroscopy and careful modeling of line profiles. For Stephenson 2-18, no rotation measurement has been published, so we do not know whether rotation is playing a significant role. Future observations could address this. What would a rotation measurement tell us? It would constrain the angular momentum budget of the star and help discriminate between different evolutionary scenarios. If the star is rotating slowly, it suggests that angular momentum was lost during the main sequence or post-main sequence phase, possibly through magnetic braking or through tidal interaction with a companion. If the star is rotating rapidly, it suggests that angular momentum was conserved, or that the star accreted material with high angular momentum from a binary companion. Either way, the rotation rate affects the internal structure and the predicted supernova properties. Rapid rotation can lead to asymmetric supernova explosions and the formation of jets, which might be observable as gamma-ray bursts or unusually energetic supernova. Slow rotation is more consistent with a standard core collapse scenario. The rotation rate also affects nucleosynthesis by changing the temperature and density profiles in the burning shells. So measuring rotation is not just a detail, it is a key input to the full evolutionary model. Now consider the observational challenge. Stephenson 2-18 is faint in the optical due to heavy extinction from interstellar dust. Most observations have been conducted in the infrared, where the star is brighter and the extinction is lower. Infrared spectroscopy can measure molecular absorption lines from species like carbon monoxide, water, and titanium oxide, which form in the cool outer atmosphere. The line profiles can reveal velocity structure, but separating rotation from pulsation, convection, and wind outflow requires multi-epoch observations and detailed radiative transfer modeling. The signal-to-noise ratio must be high enough to detect subtle asymmetries in the line shapes. Current infrared spectrographs on large telescopes can achieve this for the brightest red supergiants, but Stephenson 2-18 is not among the brightest. JWST's NIR, SPEC, and MIRI instruments have the sensitivity to obtain high-quality spectra, and observing proposals targeting red supergiants in the Stephenson 2 cluster are likely being considered or have already been executed. When that data becomes available, it will significantly improve our understanding of the star. Here's what to expect from the results. If JWST spectroscopy detects molecular lines with resolved velocity structure, it will map the kinematics of the outer envelope and wind. If the lines show systematic shifts or asymmetries, it could indicate rotation, large-scale convection cells, or asymmetric mass loss. If the abundance ratios differ from solar or show evidence of CNO processing, it will confirm dredge-up and constrain the mixing history. If the spectrum includes emission lines from the circumstellar shell, it will reveal the physical conditions in the wind and the efficiency of dust formation. All of this data will feed into refined models of the star's current state and evolutionary track. The models in turn will make predictions about the supernova properties, which can be tested if and when the explosion occurs. This feedback loop between observation and theory is the engine of progress. Notice how it ties back to the original question. The biggest star ever discovered is not just a curiosity, it is a test case for stellar physics. Stephenson 2-18 challenges our models to explain how a star can grow to 2,000 to 2,600 solar radii without flying apart. The answer involves a delicate balance between radiation pressure, mass loss, pulsation, and the thermodynamics of a cool, extended envelope. The star exists at the boundary of what is possible, and by studying it, we learn where that boundary is and why it exists. The same principles apply to other extreme objects in the universe. Black holes at the upper end of the mass scale, neutron stars at the density limit, white dwarfs at the electron degeneracy threshold. In each case, the extreme pushes the physics to a regime where approximations break down and details matter. Stephenson 2-18 is extreme in size, but the underlying physics is the same as in smaller stars. It is just amplified and made visible. What does that reveal about the unity of astrophysics? It shows that the same fundamental processes, gravity, radiation, nuclear fusion, thermodynamics, govern everything from planets to galaxies. The equations that describe hydrostatic equilibrium in the Sun also describe it in Stephenson 2-18. The difference is in the boundary conditions and the relative importance of different terms. By exploring the full range of parameter space, we test whether our equations are general or whether they need modification. So far, stellar evolution theory has passed every test, with adjustments and refinements along the way. The discovery of Stephenson 2-18 and other extreme red supergiants fits within that framework. They are not anomalies. They are predictable consequences of the theory. But predictable does not mean uninteresting. Here's why. Predictable phenomena still require measurement to confirm. Theory tells us that red supergiants should exist and should have certain properties. But until we observe them and measure those properties, we do not know for sure. Observations also reveal details that theory cannot predict from first principles, such as the exact mass loss rate, the chemical composition of the wind, the amplitude and period of pulsations, and the structure of the circumstellar shell. These details depend on microphysics and initial conditions that vary from star to star. Stephenson 2-18 has its own unique history, and studying it adds to the library of cases that inform our general understanding. The more cases we study, the better we can distinguish between universal patterns and contingent details. What does the current evidence suggest? The evidence suggests that extreme red supergiants are a predictable outcome of massive star evolution in environments with near-solar metallicity. They form from stars with initial masses in the range of 15 to 25 solar masses. They evolve through core hydrogen and helium, burning on the main sequence. They expand into red supergiants as they enter shell burning. They lose mass at rates of 1/10,000th to 1,000th of a solar mass per year. They reach maximum radii around 2,000 to 2,600 solar radii, and they end their lives in core collapse supernovae, or direct black hole formation within a few 100,000 years. The scatter in these properties is small enough that we can speak of a typical red supergiant evolution, but large enough that individual objects show variation. Stephenson 2-18 is at the upper end of the size distribution, but it is not an outlier. It is part of a continuum. So what have we learned? We have learned that the universe allows stars to grow to radii more than 2,000 times that of the Sun, but not much larger. We have learned that this limit is set by the physics of radiation-driven winds and pulsational instability, not by an arbitrary cutoff. We have learned that measuring the properties of such stars is difficult and requires combining multiple techniques: interferometry, spectroscopy, photometry, distance estimation, and evolutionary modeling, each with its own uncertainties. We have learned that the uncertainties are large but manageable, and that future observations will reduce them. We have learned that extreme red supergiants are rare but not unique, and that they play an important role in galactic chemical evolution. And we have learned that studying them tests our understanding of stellar physics in a regime that cannot be reproduced in laboratories. The next breakthrough could come from any of several directions. It could come from improved distance measurements that shrink the uncertainty in radius. It could come from time domain observations that catch a red supergiant in a pre-supernova outburst. It could come from JWST spectroscopy that reveals unexpected abundances or velocity structure. It could come from detecting a supernova from a known red supergiant progenitor and matching the explosion properties to the pre-explosion data. Or it could come from theoretical work that refines the mass loss prescriptions or develops better models of convection and pulsation. Each of these paths is being pursued, and each will contribute to the overall picture. The question is not whether we will learn more, but what we will learn and how it will change our models. Here's the key takeaway. Stephenson 2-18 exists at the edge of the possible, where the physics of stellar structure is stretched to its limits. Its size is not a coincidence or an accident. It is the natural consequence of how massive stars evolve when they have exhausted their core hydrogen and are burning helium in a shell. The star is unstable, losing mass rapidly, and will soon end in a catastrophic explosion that will briefly outshine its entire galaxy. When that happens, it will enrich the surrounding space with the elements that were forged in its core, contributing to the cosmic cycle of birth, death, and renewal. Until then, it stands as a monument to the power of gravity, fusion, and radiation, and as a reminder that even in a universe governed by strict physical laws, there is room for the spectacular and the extreme. The next observation that would settle the biggest remaining uncertainty is a precise, multi-wavelength interferometric map of the photosphere, combined with an independent distance measurement from trigonometric parallax. That would tell us, once and for all, just how big the biggest star really is.